Hello, everybody. This is the final little bit of content for the Physics 3300 course, which won't be anywhere close to a full lecture, but we're just going to finish off the content on surface gravity waves. So as usual, we're going to start with a little bit of review of where we left off. So we're talking about surface gravity waves, and this is the system highlighted over here, where we have a fluid that's infinitely deep and has a free surface here. So the average position of the surface, or the flat surface, is at the height z equals 0, but then the actual surface, because we have waves, is at the height eta, which depends on x and t, and that characterizes the surface waves. And so over the past few classes, we worked out the equations of motion that describe these surface gravity waves, or SGWs, as we abbreviate them sometimes. And we had two types of equations. We had equations like the momentum equation, the mass continuity equation, and these are equations that describe how the fluid behaves in the bulk, which means away from the edges, or away from the surfaces. And then on top of that, so these are these momentum equation here and the mass continuity equation, or incompressibility condition, on the left there. And then we also had boundary conditions. And so these two other equations were, we called them boundary conditions. And basically one of them is a boundary condition on the pressure that says at the surface, this is this one here, that at the surface, the pressure needs to equal the atmospheric pressure. And so this basically says that the pressure evaluated at the surface has to be related to the height of the free surface. And this came from the idea that the surface pressure has equal atmospheric pressure. And then our other boundary condition was that when the surface is moving, so if the surface is moving up and down here, the idea is that there must be a velocity associated with that movement. So if the surface is going up, and so eta is increasing, that means you must have a positive vertical velocity that's basically carrying the surface as it moves. And so this second boundary condition is relating the vertical velocity at the surface to the rate of change of the free surface at that particular point. And so on the right-hand side here, we have boundary conditions, and on the left-hand side, where we had equations of motion. And so that was the way we described this last time, was that was really the physics of the system. So all this work we put in, we were able to turn the physical concepts that are relevant to the system, things like conservation of momentum, conservation of mass, consistency of the pressure forces, and consistency of the dynamics of the surface. We were able to combine all those pieces of physical information into a set of mathematical equations. And now we're done with that step, and then the next job that you have is to try to solve those equations and predict and understand what do those equations actually predict about the behavior of the system. And so last time we started this, but we did not finish it. And so what we did last time was we boiled our equations down. We combined all of our 5 main equations, and we got to, or at least I think we combined 3 of them, and got to this equation here, which says that d squared p prime dx squared plus d squared p prime dz squared equals 0. And we wrote an ansatz for this that I forgot to write this here, but that p of x, z, and t was equal to a wave component. So this is a traveling wave in the x direction, multiplied by a structure function. So we have a traveling wave here, traveling wave, and a structure function. And when we made that ansatz, we were able to derive the solution based on that on the right-hand side here. And so we have, this is as far as we got with our derivation, that we found that the pressure field, the anomalous pressure field, or the pressure, the contribution to the pressure field due to this surface wave is given by a coefficient, which is equal to the density times gravity times the size of the free surface disturbance, eta naught, times a piece e to the kz, times sine of kx minus omega t. And so this e to the kz part, this is exponential decay. because z is negative as we go deep in the ocean, and so this is e to the minus a negative number, and so as z gets larger and larger, z becomes more and more negative, say negative 1,000 meters, negative 4,000 meters. This becomes e to the minus 4,000 or whatever, and very, very small. So we have an exponential decay part multiplied by a wave part. And that result came alongside the result for what the free surface looks like, and this is the second equation, that the surface eta prime of x and t, so the undulations, the waves, the movement of the free surface itself, is given by just a constant, eta naught, times sine of kx minus omega t. And so this is where we got to last time. Equations for the pressure and for the surface itself. But then there are a few questions that are left here. So one thing is we don't know the dispersion relation. So the dispersion relation is it relates omega and k. And we don't know that yet, and so we're going to get this equation. So basically, this k and this omega, they're not arbitrary. They can be related, or they in fact, they must be related. And so we're going to take a look at that. And the other thing we don't know is we don't know u prime or w prime. We haven't figured out formulas for these velocities. And so that's what we're going to finish off today. Okay, so we're going to do... we're going to find formulas for u and w, find the velocity formulas to complete our picture of how the waves look in terms of all of the variables. We're going to do that. And then second, we're going to do the dispersion relation. So our first topic for today is finding the surface gravity wave velocity. Okay, so our equations for surface gravity waves were these: dw prime dt equals minus 1 over rho naught dp prime dz. And we recall we had p prime of x, z, and t equals rho naught eta naught g e to the kz sine kx minus omega t. So since we know what the pressure looks like, we can use these two equations to just solve for what the velocities must look like. So let's do u first. So for u, we have du prime dt equals minus 1 over rho naught d by dx, and then plug in our formula for pressure, rho naught g eta naught e to the kz sine of kx minus omega t. And so that gives us, our rho naughts can cancel here, so we get minus g eta naught e to the kz. Then the derivative hits the sign here, so we get cosine of kx minus omega t multiplied by k. So we have partial u prime partial t equals minus g eta naught k e to the kz cosine kx minus omega t. And now we can integrate. So integrate both sides with respect to dt. And so we get u prime of x, z, and t equals minus g eta naught k e to the kz. And then cosine turns into sine under integration. And then we have to multiply by negative 1 over omega because of the sort of chain rule in reverse. And so we get here g eta naught k over omega times e to the kz sine kx minus omega t. And that's our formula for u prime of x, z, and t. And for w, very similar approach. So for w, we have dw dt equals minus 1 over rho naught d by dz of, we put in our formula for pressure, so we get rho naught g eta naught e to the kz times sine kx minus omega t. And so again, our rows are going to cancel. So we get minus g eta naught. The derivative now hits e to the kz, so we get k e to the kz back times sine kx minus omega t. And so we have partial w prime partial t equals minus g eta naught k times e to the kz times sine of kx minus omega t. And now again, we can integrate both sides. And we get w prime of x, z, and t equals minus g eta naught k e to the kz. And then sine integrates to negative cosine. And then we again multiply by minus 1 over omega. And our final result here is we get minus g eta naught k over omega times e to the kz times cosine of kx minus omega t. And that's w prime of x, z, and t. Okay. Okay. So now we have formulas for all of our wave variables. We have, so we now have formulas for p prime, eta prime, u prime, and w prime. So all four of our dynamical variables that describe our wave, we have explicit formulas for them. So to obtain the dispersion relation, which relates the angular frequency dispersion relation for k and omega, we can use the surface boundary condition. Which was that w prime of x, z equals 0, and t should equal partial eta prime partial t. So we can just simply evaluate these two expressions, because we had here eta prime of x and t was eta naught sine kx minus omega t, and w prime is just right there. So w prime at z equals 0 is the same as minus g eta naught k over omega e to the k times 0 times cosine of kx minus omega t. And that should equal d by dt of eta naught sine of kx minus omega t, which is eta naught times k times cosine kx minus omega t. And so looking at the two sides of this equation, we see that the cosine part can cancel, the k part can cancel, the eta naught part oh, I'm sorry. Yes, I made a mistake here. So let's just sorry, I took the time when I took this derivative. I took the x derivative, and I meant to take the time derivative. So let's just fix that. So we take the time derivative. So this equals eta naught times cosine kx minus omega t multiplied by minus omega. So right, so when we take the time derivative, we take the derivative of the sine function, that turns into a cosine, and then we multiply by the inside part. So my mistake there, but so now our equation is g eta naught k over omega. The cosines on each side of this equation are going to cancel. So we'll get equals minus eta naught omega. And now we can see that the minus sign and the etas are going to cancel. And so we can write this as gk on the left-hand side equals omega squared, or it's more conventionally written omega squared equals gk. And this is the dispersion relation for surface gravity waves. And so just like we had for sound waves, so recall, for sound waves, we had omega squared equals cs squared k squared. And what we said was that the wave speed, c, is omega over k. And so that meant that omega over k squared, which was the wave speed squared, was just equal to this parameter cs squared, which was gamma p naught over rho naught. And so what that meant is that all of the waves, sound waves, they all have their phase speed equals this constant parameter called the sound speed. But so now what's going to happen in our case now for shallow water gravity waves? So for shallow water, for deep water waves, for surface gravity waves, we instead have omega squared equals gk. And so we can write this, we can divide both sides by k squared. And so we get, so our phase speed is omega squared over k squared equals gk over k squared, or c squared equals g over k. And so as a reminder, lambda, the wavelength of the waves, is 2 pi over k. So we can write this as g divided by 2 pi over k over lambda. Or c is equal to the square root of lambda over 2 pi times g. And so what this shows is that, so we have c here equals the square root of lambda g over 2 pi. And so what this shows is that the speed of surface gravity waves actually depends on the wavelength, and that the speed gets faster the longer the wavelength is. And so what that means is that shorter waves with periods of say, wavelengths of a few meters, they propagate relatively slowly, but very, very large waves with long wavelengths can travel very, very quickly. So just as an example, so let's consider short waves with a lambda equals 1 meter. So here's our surface, and then we have some relatively short wavelength waves. So that means that our k is 2 pi over lambda equals 2 pi per meter. G is 9.8 meters per second squared. So our wave speed is the square root of 1 meter times 9.8 divided by 2 pi, which works out to about 1.2 meters per second. Now, longer wavelengths are called swell. So for longer waves, so short waves travel at about speed of about 1 meter per second. But longer waves, which are often called swell waves or just swell, these would look something like this. So very long waves where the wavelength is quite long. Here the wavelength is very short. And so let's say lambda equals 100 meters. So in that case, we would have c is equal to the square root of lambda g over 2 pi is the square root of 100 meters times 9.8 over 2 pi, and that works out to about 12 meters per second. And so this is much faster. So long waves travel faster. And this means also that surface gravity waves are dispersive. Because a wave being dispersive means that the different wavelength components of that wave all travel at different speeds. And so for sound waves, we found that all the different wavelengths in the sound waves all travel at the same speed, and so that's why they're called non-dispersive. But sound waves have a different property because their wave speed depends on the wavelength. And that means that they sort of break up and spread out into their different wavelength components as they evolve, because the longer wave components, they run out ahead of the other wave components and propagate away more quickly. And this is actually something that you can see when you observe storms. So we can actually observe this from space, for example. And when there's a storm, if you have a let's say here's the ocean, and you have some kind of storm over the ocean, it's generating waves, and then you have an observer very far away. What's going to happen is, near the storm, you're going to have shorter period waves, a shorter wavelength, and then as you get further away, the swell waves are going to propagate faster out. So this observer is going to see the long waves arrive first, because those are the ones that have the fastest speeds, whereas these small scale waves are slow, that are near the storm, and they take a long time to propagate, whereas these waves are fast. The broad swell waves propagate away from the storm more quickly. Okay, so that's it. So we basically talked about how to figure out formulas for the different velocity components of the wave, the u and w velocities, and then we combined these formulas to derive the dispersion relation. And so for sure, you want to make sure you have an understanding of what a dispersion relation is. It's a formula for a wave that links together the temporal properties, like the frequency or the period of the wave, with the spatial properties, which is the wavelength or the wave number. And so waves, whether they be sound waves or whether they are surface gravity waves, they don't have arbitrary wavelengths and periods. That the wavelength and period are related to each other. They're related by the physics that governs the wave propagation, and that relationship is encoded into the dispersion relation. And then you can also use the dispersion relation to determine the wave speed, because the wave speed is omega over k. And so from the dispersion relation relating omega and k, you can generally compute this ratio, which tells you how fast the waves travel depending on their wavelength. Okay, so I will post practice problems and some lists of topics. And if you have any questions about this lecture or anything in the course, please just let me know, and I'm happy to either answer questions over email or to have a meeting. And so best of luck with your preparation.